We'll try something new today. I'm actually going to try to record 2 different lectures, so I'm not for sure how that works. All right. Um, here we go. So a chi-squared test, again, it's used for categorical data. There's 3 different types that we're going to come across. We're going to learn about, and then the first, the example we just did was a goodness of fit test. We also have an independence test and a homogeneity test. And hopefully we have time today to get to the homogeneity test. Okay. But there's 2 things that we talk about here. There's observed counts and there's expected counts. And we'll get to more about that later as we see the different examples. It allows us to determine if a sort of specified population distribution seems valid. Okay. The one we're going to talk about first is that goodness of fit test that we already looked at on our calculator. We already talked about our degrees of freedom. It is the number of categories minus 1. Okay. I really don't know where I'm hearing sound at. Not that it matters, but. We'll do it there. Okay, so the test statistic used for chi-squared is going to be this. We went through it in that little table on the other page. That chi-squared value that we found is actually the sum of all of those observed minus expected squared divided by expected. Okay, so again, because it's a test, we're going to have a hypothesis. We have a null hypothesis and an alternate hypothesis. Our null hypothesis will be the population proportions are going to equal are going to be equal to the stated proportions. Now, my alternate hypothesis, this says at least one proportion differs from the stated proportions. I don't like to go that way, so usually I say it matches or it doesn't match. It fits or it doesn't fit. Okay, but it's going to be your preference on how you go about doing that. Okay, here's our chi-squared curve. Okay, so with 1 degree of freedom, we can see that's the blue line. It is clearly skewed to the right. As we continue to add degrees of freedom, which is actually adding categories. So as we add the categories, it becomes less and less skewed right. So the more categories we have, the less skewed this is going to be. Okay. The sample size doesn't have really anything to do with my degrees of freedom on this. So there's little change with the increase in sample size. We can see that this is skewed to the right. And as the number of categories increase, the chi-squared curve becomes less skewed. And I actually don't know what this means. I just have it in my notes. I'm not for sure exactly why it's there. The mean is equal to degrees of freedom, but I'm not, I know, again, one of those things, I do not know why that is there. Okay. We mentioned this already because we had done a chi-squared test, but we have 4 different assumptions down here. Again, we're going to do counts of categorical data have to be greater than 1. So we have to have at least 1 category, okay, or greater than 1. So we have to have at least 2 categories, okay. So a random sample or randomized experiment, that stays the same. Large sample size, okay. So that means my sample size, all expected counts are at least 5. So I don't know why I wrote that in. Grab the highlighter. All expected counts are at least 5. Okay, so in other words, greater than or equal to 5. And independence still remains the same. My sample size has to be less than or equal to 10% of n. Okay. Let us go try to do a chi-squared test. So in example 1, our question is, are births evenly distributed across the days of the week? So suppose Mr. Dottie looks up the birth dates of all my students, ages 84. Do these data provide evidence that births of MHS students are not equally likely on all days of the week? Okay, so does it matter what day of the week it is? Are we evenly distributed across all days? Okay, so luckily Excel has a little feature that I didn't actually take time to look up all your birthdays of the week. Okay, that'd take me forever, but I was able to search all your birthdays and then had Excel go grab all the days and then use a pivot table. I don't know why I felt the need to do that, but tell you that, but here we are. Okay. Now, when we do so we're not going to have any parameters, but we need to list off my observed outcomes and my expected outcomes. So how am I going to figure out all these expected outcomes? Last time we took a percent times my total and did it that way, but what are all these expected outcomes going to be? Sorry, what? They're going to be equal. Well, what are they going to be equal to? 84 divided by 7. Very good. So what is 84 divided by 7? 12. So all of my expected outcomes are going to be 12. So this one actually it's looking pretty good. Okay, I know we were down by 3 on the very first one on Sunday, and we're up by 4 a couple times in the middle. But I think it's going to down by 4 on Saturday. So it looks like we could balance this out. Okay, so what's my null hypothesis going to be? Observed birthdays per day of the week are the same as expected. Okay. Alrighty. My assumptions for inference. Number 1, you remember what it was? Oh, we could do random. Sorry, I already started right. Number of categories is greater than 1. How many categories do we have? We have 7 categories, 1 for each day of the week. Okay. Random sample of MHS students. Do we have that here? This is going to be a PWC because it was a convenience sample. I just went and grabbed my kids. Okay. How do I do large counts? Is my sample large enough? How do we determine that? Because all expected values greater than or equal to 5. Independent. Is it independent? So do I have a sum? I don't even have a sum. Oh, I do too. 84. $84 is less than 10% of all MHS students, so we're good to go. What degree of freedom are we going to use? Okay, so we're going to go with 7 minus 1, which is 6. Okay, so again, so now we're going to come up with a chi-squared value and a p-value. So again, we can take time to enter this into your calculator if you want. I don't know, it's a time thing. I have it in my calculator already, I believe, unless I've completely botched what my plan was. But yep, there we go. L1 and L2 contain my observed values and my expected values. Okay, so again, we're going to go into stats. We're going to go over to a test. We're going to arrow up till we get to the goodness of fit test. The goodness of fit test is generated from list, and my list is L1 and L2. So there we have it. My degrees of freedom was 6, and we're ready to calculate. Okay. Now, so we end up with a chi-square value of 5.1, which is not very big. Previously, we had 50 something. So let's go back and talk about that second while it's fresh in my head. So here's that chi-squared value that we just calculated. Okay. In our M&M example, what was our chi-squared value? 53. Well, there's 16 right there. Okay, so where's 53 going to be at? Way the heck over here. So that means that the probability of that actually happening is super small. And that's why we got some number times 10 to the negative 10th, because it just is not going to happen. Here we got a chi-squared value of what? It was 5 something. So that puts us right there. So that means there's going to be a little bit of area to the right-hand side. There's a pretty good probability this happens. My degrees of freedom was what? 6. So that means my curve is even less skewed. So that's almost like right in the middle of my curve. And from our p-value, that's actually how it came out. So again, it's understanding which curve we're looking at in doing this. Okay. So if we come down here, we got a chi-squared value of 5.17. However, I'm jumping the gun on the chi-squared value because we do have to show mastery of the formula. So we're going to have to go with 9 minus 12 squared divided by 12 plus. So all we need is the first and last terms. And we ended up getting a chi-squared value of 5.17. So that means that we ended up having a p-value of 0.523. So sure enough, it was more than half. Okay, more than half of the curve still existed to the right. So given my null hypothesis is true, in this case that my birthdays are evenly distributed across all days of the week. Okay, given that's true, we're going to see this outcome 52% of the time. So therefore, that's not statistically significant at all. So our conclusion is, since our p-value is greater than alpha, did we establish alpha anywhere? It does not look like we did. So we're going to say alpha is 0.05. And again, even though we're talking about a chi-squared test versus a t-test versus a z-test, we're still going to reject or fail to reject. There is insufficient evidence to suggest that birthdays do not match even distribution. Oh, getting ahead of myself. Okay, we reject the hypothesis that days of the week and birthdays is different if chi-squared is relatively large, small, or both. So if we're going to reject it, that chi-squared value needs to be large. Okay. If each observed frequency equals the expected frequency, what's going to be the value of chi-squared? We already talked about that, but yes, 0. Okay. Example 2. Looks like we got 3 examples to cover. Does the warm, sunny weather in Arizona affect a driver's choice of car color? Cass thinks that Arizona's drivers might opt for a lighter color in the hope that it will reflect some of the heat from the sun. To see if the distribution of car colors in Oro Valley near Tucson is different from the distribution of car colors across North America, she selected a random sample of 300 cars in Oro Valley. The table shows the distribution of car colors for Cass's example in Oro Valley and the distribution of car colors in North America according to whatever ppg.com is. I flat out stole this from someone else's note packet, so I don't know what PPG is. Personal protective gear, but I don't think so. Okay. Do these data offer convincing evidence that the distribution of car color in Oro Valley differs from the North American distribution? Okay, it's a yes or no question, so that means a test. Okay, we need to know what type of test to do. This is going to be categorical variables, so that means it's going to be a chi-squared test. And since I'm seeing if my sample matches something else, we're going to do a goodness of fit test. Okay, so again, if you want to, you can still run through our phantoms. I will leave that up to you, but there are no parameters here, so we're going to start out with our hypotheses. Our null hypothesis is the distribution of car colors in Oro Valley is the same as the national distribution. What's our alternate hypothesis going to be? Assumptions. So again, we have how many categories? 1, 2, 3, 4, 5, 6, 7, 8 categories. So categories is greater than 1, so we're good there. Expected counts is greater than or equal to 5. Whoops. I don't know that. Okay, how am I going to know that? I have a sample of 300 cars. I'm going to expect 23% of them to be white. And if I take 23% of 300, that gives me a 69. So I would expect 69 cars to be white. Using that same principle, I'm just going to fill out my expected row. Sorry, what? You could just look at the lowest value. However, I need my expected outcomes as part of the answer. So my expected outcomes have to be written down to get full credit. Plus, we need them to make a list out of anyway. So yes, the green car almost messed us up. So we survived though. We do have a random sample of cars in Oro Valley that was stated. And lastly, this is going to be independent because I'm assuming that 300 is less than 10% of all cars in Valley. Now, again, it doesn't matter where this is at. I probably actually should, we talked about it from the very beginning. This is a chi-squared test. Again, we're going to write goodness of fit behind it because we don't, that's for me. AP test wise, don't put anything behind it. Just write down chi-squared test and call it good. Okay, next. So what we're gonna have to do, and just to save time, we're not gonna do it, but this is gonna be L1 and this is gonna be, nope, that's not gonna be. This is gonna be L2 in my calculator. Okay, so again, we're gonna enter my observed value, we're going to enter my expected values, and we're gonna run that goodness of fit test. Okay, so my chi-squared, what would be my contribution calculations here? We observed 84 white cars. How I expected 69 cars. We're going to square that difference and divide by the expected, which was 69. So there's term number 1. Now I need that last term in there. We observed 39, but we expected 21. So we're going to divide that also by 21. So there's going to be some larger values in here probably. All right. Other is going to count for a lot. Okay. Green turned out okay, but if we did that, so this is where I'm going to go to my calculator. I'm going to choose the chi-squared goodness of fit test. I'm going to have both lists in there, and we're just going to run it. I'm going to, deny you of that opportunity to watch me do that. So here it is, 29.92. So before I write the p-value up here, is that p-value going to be small or large? Because my chi-squared value is 29.92. That's very large. So that means my p-value is going to be very small. Okay. In this case, my p-value is 0.00098. Now, I did not show you how we could do this by hand yet. Okay. So let's jump out. I'm going to jump out and we're going to look at our table real fast. So we got to remember 29. I don't even know if 29.92 will be on there, but we'll look. Okay. So we're going to go out to the where are you at? Formula sheet. Okay. How are we going to use a chi-squared formula sheet? Okay. So how many degrees of freedom do we have on this? We had 7 degrees of freedom. So here's 7. I wanted to be how confident? We never talked about it, but we wanted to be 5% confident. So there's the, we're going to work with this in 2 different ways. There's the critical value. So if my chi-squared value is over 14.07, that means it's going to be statistically significant. Okay. In this case, we had what, 29? Okay. That's why my p-value is very, very small. This is not going to give us very nice percentages. So what was my chi-squared value here? Was it 29? So we're going to go across on row, what was it, 6 degrees of freedom? I already forgotten. 7 degrees of freedom. We need to write that down. So I go over here. My chi-squared value was, it was like over 29, right? So that means that the highest this value goes is 26. But if I go up, here is my probability. That would be a 0.005. So I know that the p-value is smaller than 0.0005. And that's the best I can do with a table. Okay, it is not necessarily very good. The other way of hand calculating a chi-squared value is if I go into my distribution. So I go second in a distribution. Okay, if I look there, there is a chi-squared CDF. Okay, I could choose that. And so my lower boundary was what, the 29, was it 0.992? Well, it's going to be today. My right boundary is very, very large. I'll just leave it at that number. How many degrees of freedom did we have? 7. So this would be, again, the hand entry. And I don't know, I forgot to quit first, you stupid thing. Okay, and there we go. So there is the 0.00009 that I told you the p-value was. So we can do the p-value. We can do a hand calculation here, but I just think there's zero reason when your calculator does it for you. Okay. All right, so let's go back to our notes. So if we were going through phantoms, we have done our hypotheses, we've done our assumptions, we've named it, we've found a test statistic. Remember, our test statistic is the chi-squared value. We've obtained a p-value. It's very, very small. So we're ready to make a decision. Okay, so we're still going through the same exact thing. Sense, if you could read that, that was a sense. It's like smins. I know, I forgot the sense. I don't know why I put the equal sign either. Since the p-value is less than our alpha level. Did we establish alpha anywhere? Or did it tell us? It did neither. So I'm going to write alpha is 0.05. The other thing I don't have in here is I didn't include my degrees of freedom. Okay, so again, I got to have that stuff listed. So because that p-value is small, we're going to reject the null hypothesis. There is insufficient evidence to suggest what? Sorry, my bad. There is sufficient evidence. There is sufficient evidence. My brain is lost. There is sufficient evidence to suggest that the color distribution in Oro Valley is different from the national distribution. Okay. A company says it's a premium mixture of nuts, contains 10% Brazil, 20% cashews, 20% almonds, 10% hazelnuts, and 20% peanuts. You buy a large can and separate it. Upon weighing them, you find there's 112 grams of Brazil nuts, 183 grams of cashews, yada yada yada. You wonder whether your mix is significantly different from from what the company advertises. So why is the chi-square good as a fit not appropriate here? Why can't we run a goodness of fit test on this? Oh no, there's actually like 5. We have Brazil nuts, cashews, almonds, hazelnuts, and peanuts. So there's plenty of categories. When we talked about M&Ms, we talked about the number of blue M&Ms we've got on our plate, right? When we talked about cars, there was 52 white cars in the lot. What's our issue here? Yeah, it's not, well, it's categories, it's not counts, it's weights. Okay, that's our problem. What might we do instead of weighing the nuts to use chi-squared? Well, obviously then we would count the nuts. So I don't know. I mean, you might be able to do some type of matched pairs t-test with this. It didn't quite follow into nice neatness as far as we want to do a mean, and it's not means, so it has some other issues there. All right, last year, Mrs. Sepp was selected as a potential juror for federal cases in Topeka. Although she obviously is very young, she believes that in general, older people are overrepresented on juries. The table gives information about people selected on federal juries in Topeka, Kansas. Does it appear that these jurors were selected at random from an adult population of Kansans? Okay, so again, since we're doing with categorical variables, this is telling us to do a chi-squared test because I'm comparing my sample versus something that was given. This is going to be a goodness of fit test. We'll just get these out of the way now. My degrees of freedom, I have, looks like 1, 2, 3, 4 categories. So 4 minus 1 is 3. So we have 3 degrees of freedom. And we'll test at an alpha level of 0.05. Okay, Sammy is concerned. Our null hypothesis is observed counts of jurors of each age group fit the population percentages. Our alternate hypothesis is All right, so in order to determine that, I have to have some observed counts and some expected counts. So how am I going to find an expected count? How many would I have a jury of looks like 66 people. How many would I expect to be age 21 to 40? Yes, it would be, again, we're taking 42% times 66, and that gives me 27.72. And I actually have all these written down, so I will just give them to you and spare us the pain of all those calculations. All right. Okay. So now we're ready to go. Again, it's following Panic if you want to follow, not Panic, Phantoms, if you want to follow Phantoms, or we just know what's next. Next is my assumptions. Can we do this? Category counts greater than 1. Do we have more than one category? True. We have 4. And I would assume that's, can't spell the word juror, looks like. Oh, speaking of which, I'll write that down. I got my prospective Riley County juror survey that I had to fill out before spring break, and I forgot to fill that out. Yeah, I imagine if you had reason enough to, I mean, it's crazy. You get to the courthouse, and I've seen a guy go, I am completely blatantly sexist, and I will automatically say that she's guilty no matter what. I've had people, and I've seen people say that during the juror selection process just to get kicked out of the process. It's stupid. Sorry, I just one of those. It's your right it's your duty as a citizen to be part of that process. So I know some people don't like it, but I've been a head juror before. It's an interesting process. We do have a random sample of jurors. I forget this is being recorded, but oh well. Okay. What's our next one? Large counts. My expected values are all greater than or equal to 5. That is true. And lastly, independent. So 66 is less than 10% of technically all Kansans would be available for a federal jury. Okay, so chi-squared. I observed 5. Expected 27.72. Observed 19. No. I observed 33. But I expected 12. Not looking good for the home team. So again, if we were doing this, we would enter this into list 1, we would enter this into list 2, and we'd run that goodness of fit test, and our chi-squared value turns out to be 61.27. Huge chi-square value. So my p-value is actually close to 0. I mean, that's super small. I don't know what I didn't even look at the exponent. I don't think this is from last year's notes, so I didn't even type it in. Times 10 to the 13th, wow. Since our p-value is much smaller than alpha, we will reject HO. There is sufficient evidence to suggest age proportions of jury do not match population proportions. Okay. Some discussion questions. If you switch the order of the categories, what's going to happen to your chi-squared value? Meaning if you put 61 and older as your first category and then 51 to 60 as your second category, what's going to happen? The value of your chi-squared value does not change. Is that true then? That is true. The observed counts are always whole numbers. You're counting something. So yes, that is true. Your expected counts are always whole numbers. That is false. They can be decimals. The number of degrees of freedom is one less than the sample size. It is what? And a high chi-squared value indicates a high agreement between the observed frequencies and the expected frequencies. Okay. All right, I'm going to stop this recording.